Hello, everybody. Welcome to my talk. I'm Huibo Wang, a senior researcher from Baidu Security. Today, I would like to discuss with you about our work, multi-certificate attacks against proof-elapsed-time and their countermeasures. This is a collaborative work between Baidu Security, SGTU, SUS Tech, and Ohio State University. This talk is about the security of blockchain, especially the security of the key role of blockchain, the consensus mechanism. What's a blockchain consensus mechanism? The blockchain consensus mechanism refers to methodologies to achieve agreement of rules, determining which blocks and transactions are valid across a distributed network. In the context of the Bitcoin blockchain, it's known as Proof-of-Work. Hyperledger Sawtooth has proposed another consensus, named Proof-of-Elapsed-Time. As the soul of blockchain, once consensus is broken, attackers can manipulate blocks and transactions, which will lead to serious consequences, such as double spending in Bitcoin. Well, proof-of-work is to prove a certain amount, a specific computational effort has been spent. Proof-of-elapsed-time proves a certain amount of time has elapsed. In proof-of-work, the first miner solving the computational puzzle will be the winner of the leader election, be able to commit a block, and be rewarded. Well, in the proof-of-elapsed-time, the miner with the shortest waiting time would end up to be the winner to commit a block and be rewarded. For both of proof-of-work and proof-of-elapsed-time, the core principle for them is fairness. Fairness means each node in the blockchain network has the same opportunity of winning the leader election. Since proof-of-work utilizes huge amounts computing power for unuseful hash computation, significant computing resources are wasted. Proof-of-elapsed-time proved to be more power efficient compared to proof-of-work. And also, it's more scalable. Proof-of-elapsed-time looks promising. However, we determined a couple ways that the protocol can be attacked, breaking its fairness. Before I introduce our attacks, I will give an overview of how proof-of-elapsed-time works. In short, proof-of-elapsed-time can be divided into three distinct steps: sampling a random waiting time duration, waiting until the waiting time duration elapses, generating a certificate that proves the time elapsed, and signing it with a POET private key protected by Intel SGX, which is a hardware-enabled trusted execution environment. The random waiting time duration is protected by Intel SGX with integrity and confidentiality. Therefore, achieve the fairness of proof-elapsed-time. The timestamp of the duration is provided by Intel CSME, Converged Security and Manageability Engine, which is an embedded subsystem in Platform Controller Hub and is trusted. Intel SGX is also used to assure that the certificate is only generated when the time elapsed, and the certificate is signed by the POET private key protected by SGX. Therefore, trustworthiness is assured. Let's take a look at overflow of a POET node. There are 17 major steps in the POET node workflow. We separate these 17 steps into 3 stages. Stage 1 includes steps 1 to 7. It samples a random waiting duration, as we mentioned earlier. Stage 2 includes steps 8 to 9, representing the phase of waiting for the random duration. Stage 3 includes in steps 10 to 17, where the node generates a time elapsed certificate. The reason for this workflow's success is based on the following 2 assumptions exclusively made by POET. Assumption 1, date cannot be modified or inspected inside SGX enclave, and code in there cannot be modified either. Assumption 2, the trusted timer and the monotonic counter service provided by Intel CSME are trusted. In specific, the adversary cannot manipulate the clock ticks and counter values. From the attacker's viewpoint, their goal is to break the fairness of POET. Our work broke the fairness of POET with 3 different attacks. Among them, 2 attacks are mitigated by Intel Hyperledger later, but the last one is a POET fundamental attack that cannot be solved. Therefore, we proposed a new POET design that can mitigate all 3 attacks. When we examined the POET thoroughly, we found a hidden assumption of POET beside the exclusive assumptions. That assumption is nodes in the POET network have to follow 1 to 17 steps strictly without any interference, which means one node can only generate 1 random time duration and 1 certificate in each block election round. Then a key question comes out. What if a node doesn't strictly follow steps 1 to 17? Would it then generate multiple random duration per round? The answer is not clear yet. Then we found there's also another hidden assumption that the random duration is in fact a pseudo-random duration generated by 3 non-manipulative seeds: enclave-specific sealed key, node-specific validator address, and the current head block's certificate ID. However, we found the node-specific validator address can be modified by directly changing it as enclave input. And this allows us to control the node-specific validator address. Understanding this, we can see a node definitely could generate multiple random durations per round if it doesn't strictly follow steps 1 to 17. So, by controlling a validator address, attackers can control the pseudo-random duration generation process. Attackers can simply repeat steps 1 to 7 with different validator addresses to get multiple random durations. So, attackers can pick the smallest one instead of just use the only one. And this capability of selection breaks the fairness. This is our attack 1, parallel MCAs against the current round. We reported this attack to Intel Hyperledger, and later they came up with a mitigation. They record validator address, the seed of pseudo-random in the certificate, so other nodes in the network can verify the correctness since they have the copy of it. Later, there are other key questions coming out. What if a node doesn't strictly follow steps 1 to 17? If a node could generate multiple certificates per round? If so, could multiple certificates break POET's fairness? Well, since the mitigation mentioned before makes the breaking fairness of the current round impossible, then the second question is specific as to whether we can break the fairness in the next round. The answer to these 2 questions are definitely yes. Here comes our second attack, parallel attack MCAs against the next round. We found that since the monotonic counter value is increased after getting a time step, we can bypass the monotonic counter value check, generate multiple certificates by multiple enclaves recursively by delaying the timestamp return from Intel CSME in each enclave at step 14. We reported this attack to Intel Hyperledger. Later, they mitigate this attack by increasing the monotonic counter value before getting a timestamp. So the counter value check will be invalid if there are multiple enclaves generated recursively to run step 16 before step 13. So, in summary, we have found two attacks, parallel MCAs against the current round and the next round. And the Intel Hyperledger provide mitigations for both of them. However, with the mitigations, the current POET implementation still exposes potential vulnerabilities for creating multiple certificates, which enables sequential MCAs, the fundamental attack of POET. What's sequential MCAs? Simply, it's generating multiple certificates sequentially by repeating steps 1 to 17 within the attack window. Why is there an attack window existing for MCAs? Because to a distributed network in the specific blockchain network, due to the network latency, the synchronization of all nodes in the network needs time. So there is a time window for synchronization, which is unfortunately a window of opportunity for attackers as well. The length of the attack window is the shortest current round wait time plus the shortest next round wait time among the other nodes. Sequential MCAs take advantage of this window to create multiple certificates. So to summarize, we found a new category attacks against SGX-based POET multiple certificate attacks, including parallel MCAs and sequential MCAs. Well, parallel MCAs are already patched. The sequential MCAs do not have a solution within the current design of POET. We found that the root cause that POET couldn't defend sequential MCAs is that duration is revealed to the node before the time elapsed. So the node has the opportunity to check its value and predict if the value will be in her favor. To mitigate MCAs from the design, we proposed a new POET design called POETA. POETA has 3 goals, including security, consistency, and performance. There are 3 key elements in POETA's design. The first one is concealing duration via determine after check, which will hide the final duration to the node before the whole duration time elapses. The second one is achieving the identical distribution of duration as POET, which assures the same block rates as POET to avoid forks. The third element is a trade-off between security and performance. The core idea of POETA is concealing duration via determine after check. In POETA, the duration is composed of unknown numbers of duration segments with using an oracle function for each duration segment. Attackers couldn't predict the duration before the last duration round starts. By concealing the number of duration segments, the duration is concealed before the time elapsed. We have implemented POETA and evaluate with regard to duration distribution, performance, and security. Our evaluation results show that POETA has optimal performance with stronger security and also the identical duration distribution as POET. For more details, please check out our paper. To conclude, we have found a new category attacks, multiple certificate attacks against SGX-based Sawtooth POET, including 2 parallel MCAs and 1 sequential MCAs. 2 parallel MCAs has been addressed by Intel Hyperledger, while sequential MCAs as a fundamental attack of POET cannot be resolved. We propose a secure design of POETA to mitigate all MCAs with concrete implementation and evaluation. Thank you, and happy to take questions.